Yeah,
Are you
so
recording all of them now?
yes. Well, yeah.
Yeah.
I might as well do that. Specifically, I'm recording the todays and Wednesdays because then you'll have the quiz Tuesday.
And you won't be here. Got it.
So that'll be like a bank of things. Yeah, I was gonna say for like number 9 and number 8 and stuff. Yeah, like feel free to use any resources you want.
Mm-hmm.
The biggest thing
I was just looking on Google and I found
Yes,
this thing,
good.
and then I didn't understand some of the lines of it, and I was like,
Yeah. No, that's fine. So
getting the content over it.
the biggest thing would
just
be
resize it after we.
like if you have some answer that works and you got it from somewhere, that's fine.
okay.
But just put your own comments because when I grade it, like if it works, there's sort of not much I can say. I mean, but if you put comments, those are really good. Or if it works, that's fine. But if it doesn't work and you don't have any comments, there's sort of not.
You can't add much.
I don't really know what to do with that. So if you put comments and it doesn't work, but your comments all look good, and you just forgot like a parentheses or whatever, like I don't care about that. That's so.
Got it. Yeah.
The comments are really what shows me that you like knew what you were doing, kind of thing, even if you didn't know what you were doing.
I hate coding.
So don't feel. I know a lot of people. Some people are like, "Oh yeah, I already wrote one," and some people are like, "I've never done this before." So
I had
I
to
don't
learn
want-
Python for all of like
Uh-huh.
a semester. It was awful. And we couldn't,
I understand,
our
I understand.
exams were paper, so it was
Yeah.
like, I'm like, you trial and error code. Like, that's what you do.
Yeah.
Like,
I do. I had to learn C++ on paper in physics. That's what you have to do for the first year class or whatever. I was like, why?
Literally
You had to like write a
makes no
loop
sense.
with. You had to like put a new line with this at the end, like end parentheses or whatever bracket, so you know. I'm like, and then a semicolon, whatever. I don't even remember. But I was like, what is stupid? Why would anyone do this?
That's just so much
And
work
C++.
for whoever's grading it too.
Yeah, the head of the department.
Yeah.
I don't care. Whatever you had to. Anyway, all right.
so question 9.
Yes. Which one was 9? Oh, yeah. Okay, I didn't do this. Holding 2 5-kilogram masses at arm's length. Rotates. Okay. Ah, yes.
That's just
So we just draw it. I'm gonna take out all the numbers because they're boring. But and I'll say this is the radius r, a little r, and then I'll say he has some. Actually, sorry, I just want to see one more thing. Okay, 2 mass is a distance 1 meter. So this is like ridiculous. Distance d. And I'll say he has mass big M. These have mass little m. This is like the radius.
Okay.
Yeah. So this is like the This is just a setup. I'm not gonna write all the numbers because we want to like actually show some sort of rules instead of just the answer. Okay. Well, and we're gonna assume that there's just some masses connected, but these are massless. Like his arms are massless or whatever. Like because they don't say anything about his arms being cylinders or whatever. So like we're not gonna assume that they That would be really complicated if they did anyway. So, so they want us to find. They want us to find the moment of. Well, I don't think they actually. I don't know if they say moment, but they want us to find the angular momentum, right? L.
Okay.
So let's just find L.
Yeah, it says calculate the angular momentum of a man weight system.
Yes. Okay. Good. And then he's going to pull his arms in, and then something's going to happen, right? So, yeah. So we'll do that when we get to it. But let's just say find the angular momentum now. So, and he's and everything's rotating, of course, with angular velocity omega. Let's say, of course, if it's not rotating, there's no angular momentum, obviously. So we know. Let's just write the formula for angular momentum, which we don't use that often. Like we don't. It's sort of like one of those things where you don't do a lot of problems with it, but it's very, very fundamental. It's like momentum, right? Momentum, you don't often write momentum equals something.
Yeah.
Usually, maybe use it in the problem, but you wouldn't explicitly solve for it. But it is really important because it is completely conserved in all situations that are external, like where there's no torque externally. So even if there's stuff internally happening, anyway, so it's just I omega, just like mv for momentum,
Yeah.
for linear momentum. And so, so of course we have omega here. We know if we wanted to really be careful with the vector, we know that the vector, let's say he's going around this way, the vector would actually, if you take your right hand, curl them in the direction of motion, it would be upward. So the actual vector is going upward and its magnitude this. So that's, of course, that's trivial. The hard part of this problem is to find I. So, well, what is I? Well, I has there's two pieces. Well, actually, there's three pieces. There's the person, I'll say I total, which is going to be this I.
Okay.
Well, I'll say total, is I person plus I mass. Well, so it's really I mass 1 plus I mass 2, right? It's
For each of the.
For E, right. So
Okay.
if this is mass 1, this is mass 2. But because the masses are identical and they're the same distance or all this stuff, it's actually just going to be 2 I
Makes
mass.
sense because
Okay, nothing's different about them. If they were a different distance, though, if they're different masses, we could not do this.
got it. Okay.
But because they're going to be
They're
identical,
identical, yeah.
yes.
Could you check and see if you
And
can
so,
go into Blackboard?
I person is
Seems
going to
like
be,
the
well, it's a
web page is
cylinder, right?
It is.
So it's going to be I of a cylinder, which is the same as the I of a disk.
Do you need it for something?
Disk, right? And so because a cylinder is just a disk with a long, elongation kind of thing.
And that we would get that equation from. his
Yeah, it would be given to
sheet.
you. I
Okay.
believe it's 1/2 mr squared. Yeah, so you'll be given to you. But just the thing that won't probably be, well, it might be written on there, but the fact that a disk and a cylinder are identical, there's a theorem.
Okay.
It's kind of like the parallaxis theorem, but it's a little more, sort of qualitative, I guess, where it's a little easier, which is that if you extend, it really only applies to this one case, but it's a theorem that says that if you take the angular momentum of an object and you extend it, meaning you make it longer in the dimension that you're rotating it around,
Mhm.
it doesn't change the angular momentum. It doesn't change the moment of inertia form.
Okay.
Meaning, if you have a disk or a sort of coin or a thin rod, as long as it's all rotating around here, all that is just elongating something along the dimension of rotation, the axis of rotation.
Okay.
Elongating something on that does not change the form.
Got it.
Because, well, yeah, anyway. It just specifically
It
because
makes-
there's no
yeah.
z here, right?
Okay.
It's just r, meaning the distance from. Anyway, so that's that.
Okay.
The only case this really matters in is the specific, the rod and a rod rotating like this, and yeah. Anyway, so, but notice that. Oh, this is a little tangent, but notice that if we have a rod like this, of course, that's not going to be at all the same as this.
No.
But if
But if it was flipped the other way, wouldn't it be?
yes, it would.
Okay.
But the here, if we have the right and we say, well, I'm gonna like make it go around this. This is not elongating anything along the axis, so it does not apply. This has a different angular momentum than this.
Yeah.
This we'd have to use the parallaxis theorem,
Okay.
which it's in one of the other. I don't know if you were here, but it's in one of the other videos at
Okay.
least where I show. This is 1/12 ml squared, where L is the length.
Okay, I remember that. Equation.
Okay, this
yeah.
is 1/3, and you can get them from each other by using the parallaxis theorem.
Okay.
So the parallaxis theorem explicitly will show you these two, and they actually give you these two. So anyway, so you might, I believe on he sent the email he sent with saying everything you should know.
Mhm.
It said the parallaxis theorem. So
Okay.
that's one
So that's
example.
one.
That if you follow that example, you'll be fine. I
Okay.
mean, just maybe practice it a few times. But anyway, so we have this is the disk. So this is his moment of inertia. That's done. And 1/2 mr squared. And then we have plus now 2. Now what's the moment of inertia of this mass? Well, in this case we actually do have to use the parallaxis theorem again. So when you have and we're going to pretend they're point masses. So I really should write it's really like a dot. Now the moment of inertia of a dot rotating is 0 because it doesn't have any extent.
Okay.
Doesn't have any. Nothing's really rotating. It's sort of like a point rotating. Doesn't really mean anything.
Okay.
It's a little sort of undefined. Whenever they say that things are being held and whatever, they generally assume it's a point mass. Don't assume because they don't tell you. Well, anyway, it would be really complicated.
Okay.
But it's not rotating around itself. It's actually rotating around here. So this I'm
That.
talking about like this one,
Okay, yeah.
and the distance d away. So now if this had 0, the parallaxis theorem tells us that I'll just say I for now, but it just means I around this point is I center of mass plus plus, this is all on video. Just turn this a little bit, there we go. Plus m, let's say d squared, where d is the distance from the center of mass axis to the new axis. In this particular example, I actually also called it d.
Okay.
But this d just means the distance from the center of mass axis to the new axis that we're talking about.
Okay.
Now, like I said, a point doesn't have any moment of inertia. It doesn't take anything to
So
rotate
it
a
would
point.
be md squared.
It would just, right, so I would just be m, well, it'd be, sorry, capital M.
2. Oh, okay.
Yeah, and right, and so both of them would be 2 m, so sorry, go back for it. This is md squared, d now is this actual d. This before was just a letter, and now when we plug it in, we get actual 2 md squared for both of them.
Got it.
They just add together. And again, we have 2 masses that just added together because they're both rotating the same. They also just add with the other thing because they're all rotating. So anything that's just rotating simultaneously, they fix together, you can just add their moments of inertia. So, oh, sorry, this is a little m because it's the, that's, sorry, I'm,
Okay, that's what I thought.
yeah.
Okay.
I don't want to use subscripts all the time because they get kind of confusing. So I try to use little m, big M, and unfortunately I get them confused. So
Right, because that would be the masses of each of the things that they're holding.
exactly, that's what's actually rotating in this case. It is
And that would be d squared, correct?
d squared.
Okay.
Yes, thank you. Okay. Yeah, so let me just double check all this. This is a cylinder with mega mass m and radius r, good. And this is a 2 masses at a distance d that looks good. Now, another way we could think of this actually is what if we just moved this mass over here, right? That should be pretty much the same thing, right? Because it doesn't really matter if they're opposite, maybe you think for balance. But if you put this mass here, it would be 2m at distance d, which are the same form. So
Okay.
that's good because they should be the same. So anyway, so this is our I total. Is this, right? These m's are not related to each other. They're completely separate masses.
Okay.
You could change them separately. So this is I, and of course if we want to find L, it's just this times omega.
Okay.
And there we go. So L is I total times omega as a vector. If we want to be really fancy, we could say upward or whatever, because it's sort of technically upward.
So the omega would be the revolutions per second?
Omega would be the revolutions per second.
Okay.
Yeah, is that what you said?
Yeah.
Oh, sorry.
Okay.
Yes, I'm sorry, I was thinking about L.
And
L
L
would
is
be-
that times.
Exactly. So, but this is just a number, a scalar.
Mhm.
So L is a vector with a magnitude that's completely different, has different units, for example. Actually, let's see what units L has, because we could check units, but we don't actually know what units L has, because it's sort of weird. So L, we could use any of our formulas for L. So one of the formulas is R cross P, or for linear momentum. Of course, in rotating systems, this is hard because P is constantly changing because the momentum it's going in a circle. So
Okay.
this would be hard in this case to use. This is also I omega, right? And I has units of what? Well, it's like mr squared. So it has units of like kilograms times meters squared, right? And then omega has units of like radians per second. Radians aren't actual real units, by the way. I mean, I guess you could write radians, but we sort of call them, they don't have any units. So it's omega is like 1 over seconds. So this has units of kilogram meters squared per second squared. Sorry, per second. Yeah. Okay. And that seems weird to me. No, I guess that's fine. Yeah. Yeah, okay, that just makes sense. Because it's kind of like kilogram meters per second are the units of momentum, right? Mass times velocity, times another distance, meters, is kilogram meters squared per second squared. So that makes sense. Sorry, yeah. another thing. So let's go back to torque again. I don't mean to get off track, but I just want to show you the units of torque because I realize I don't think he said them or I've said them at all, but they're a little bit weird. So torque, remember, is we could say it's like the change in angular momentum over time. This is, remember, we had Newton's third law where force is dp dt. It was one of the forms of Newton's third law. Newton's second law. And so we could use this, and this would be the units of L divided by seconds. So it would be kilogram meters squared per second squared. We could also talk about how torque is R cross F, and R has units of meters times, and F has units of newtons, which is kilogram meters per second squared, and this is the same thing. So anyway, so that's the unit of torque. In case you were wondering, it's the same as a force times meter. So this has it's like a newton times a meter.
Okay.
Called a newton meter.
Okay.
So it's a little bit weird. So this, all right, I'm not going to go into it. I'll say one thing real quick. But I could go into it, but I'm not going to because it's not relevant. But this newton times a meter is actually equal to a joule, which is a unit of energy.
Oh, yeah.
But torque is not an energy measure. So it's actually very confusing.
Okay.
Because torque has units of newton meters, but which normally is like work is force times distance, which is newtons times meters, which looks the same. But this is a joule. These are in joules, and this is not. And it's just because this is a vector and this is not. But anyway, don't.
Okay.
I didn't mean to say. In case you run into that, this is very, very, very confusing.
Okay.
So if you're doing a unit check, just don't think too much about joules, which, depending on what else the problem involves, you probably wouldn't be thinking about because they don't usually come together. But anyway, okay, sorry. Let me go back to the problem, which is that now we have the total angular momentum, and now let's say they say something like, so we have some angular momentum. I'll call this L1. I'll say it's a vector. Oh, it is a vector. So that has some angular momentum L1, and now let's say they pulled their hands in, and so now the masses are, so this is like, they're like here, and this is like d over 2, right? Sorry. Well, anyway, just pretend that these masses aren't here. Now they've pulled them in,
Okay.
and now they're at d over 2. Now, how do we find, let's say what we want to find is omega after, so omega final. Actually, I'm going to call this L initial. This is the initial, now so how do you think we're going to, if we had, this is the initial angular velocity, just like with the hands out, where this is all true, and then they pulled their hands in, then we want to find L final, we want to find omega final, the final angular velocity. It's probably going to be faster, right?
Yeah.
So what is conserved here? We could say, well, I mean, okay, well, this is actually a little confusing.
Okay.
So I probably shouldn't have asked you because this is not one of those, this is a new thing. And, okay. Yeah, I shouldn't say this because what you might want to say is like energy is conserved or something. But in fact, in this case, it's not. And the reason it's not, it is sort of overall conserved, but when you're spinning and you pull something in, that actually requires some energy. So if you just talk about the rotational energy, that's not conserved because some of it went into you, well, was taken away basically by you pulling your arms in because there's force sort of against you in your reference frame, and pulling against it to require some work, which is some energy. So energy is not conserved. Linear momentum is conserved just like normal, but like it's complicated because it's rotating, so it's always changing. But angular momentum is conserved, so we can use this. So in this case, we're going to use conservation of angular momentum.
Okay.
So that's like you've heard that before,
Yeah.
right? It's like a fact. But in this case, how we're going to use it is, and if you're ever confused, a lot of these problems, like maybe you'll know you might need to use this, or they'll tell you need to use this. and you know that statement, angular momentum is conserved, is like true. If you're ever confused about how to actually apply it, what I would do first, it seems a little stupid, is literally just to write L initial, which is initial angular momentum equals L final. Just always write that, and or P initial is P final, or energy initial is energy final. Even like you might think, yeah, well I know, but like writing that just lets you, now you actually have things to fill in. You don't have to like come up with something on your own. You know what I mean?
Yeah.
So now we can fill in. Let's just fill in. Let's forget about all this stuff. Just fill in what this is equal to. Well, L initial. Okay. L initial is just I initial times omega initial.
Yeah.
And we're going to pretend, let's just, the direction is going to be the same in all of these cases, so let's not worry about the vector part.
Okay.
And this has to be, well, L final is just I final times omega final. Right? I'm just filling in what L is. Now, in other situations, we might want to use R cross P as the other formula for L. In this case, again, the reason we don't want to use P is because P is constantly changing, so it's sort of complicated. Omega is not going to change. It's just a constant vector.
Yeah.
And now, well, initial really meant this situation. So we literally have I initial, which is just this. So it'd be like 1/2 m r squared plus 2 little m d squared, right?
Yeah.
Times omega initial. Now they gave you omega initial. I assume like you're supposed to. Well, you kind of have to know that. Or maybe they don't. Well,
Omega initial, yeah, it says rotates on a frictionless turnable at 0.5.
oh, okay. Good.
seconds.
Okay, so they tell you omega initial. Perfect. So then they say what's the final angular momentum, right? Or angular velocity.
Mm-hmm.
Yeah. So perfect. So now we have everything we need except for there's literally one variable we need, which is this one. Like we need to, it's just I final times omega final. Now to solve for this, of course, we need I final. And this is where you might think, wait a minute, why, like, when I do momentum problems, where I say momentum before equals momentum after, momentum initial is momentum final, I never write the initial mass. I never write the initial mass and the final mass, because in these problems, they're basically always the same, right? In linear momentum problems, the masses don't change, right? And because that would be it would be like a rocket or something. It has to like eject. That would be really complicated. So we don't see problems like this very often. But in rotational motion, we don't have to let go of anything. If we just change the shape, or if we just pull some masses in, we're actually changing our angular momentum, changing our moment of inertia. And that's I. So I can actually change even if the total mass doesn't change. Because it wasn't just the total mass that mattered. The total mass is m plus 2 little m. But of course, these numbers can change. And now let's actually find it. Let's find the final moment of inertia.
So if it's saying he pulls his hands in, does that mean completely at his body where there's no D?
Oh, I just made up D over 2. Yes,
so
you
like
could
it
say
says
that.
it moved his hands. I get where you're going with he's just moving it that way.
Yeah.
But in that instant, like there would be no D at that point, right? Because it's completely at his body.
Yes. So let's say that instead. Yeah.
Okay.
Because you can kind of imagine how you do this.
Yeah.
When you would just sort of replace it. Yeah. But so let's do all the way into the body because that's a little bit. Because now, all the way into the body, right, is like mm, right?
Mm-hmm.
Now there isn't D, but you can't quite just set this to be 0, because then you actually don't have 3 different bodies anymore. You actually have one
with the MMs.
Exactly. So now it's basically they're part of the cylinder now.
Okay.
Right. So now you have the cylinder, but now you have big M plus 2 little m, because there's 2 of them. And that's it, times r squared. Okay. I'm assuming that's what they need.
Okay, so then that would be, oh, okay.
And now we have literally everything given except for omega f, and we could just divide it, right?
Yeah.
Yeah, that's what I would say.
Okay.
There is some question about if you pull it all the way in, I mean, I would say this is correct.
Well, it says the weight's against his body, so that
Yeah.
would make you feel like he has no.
Yes,
There's
but
no-
but I would say that makes them part of the cylinder essentially. So
Yeah.
it's basically now he has a cylinder with a slightly higher mass.
Got it. Okay.
There was some question about basically what you said of setting D to be 0, basically.
Yeah.
Of course, we said to use people, we don't get quite the same answer. There's some question because technically, if we assume that they're point masses,
Then there would be.
and we assume that he let's say he brings them like right on the axis, technically they sort of disappear.
Got it. Okay.
So it's a little bit because
Depends where.
yeah, so that would be very mathematical and not very realistic.
Okay.
So I would say don't really assume that. Don't assume that anything weird's happening. Assume that when you pull something close to your body, like those masses, they're just adding to your. So it's a cylinder now with a greater mass. That's what I was assuming. They're going to be close.
So
anyway,
would there be torque exerted if the masses are at his body?
So there was a change in angular momentum, right?
Correct.
Sorry. Yeah, there was a change in angular velocity.
Yes.
Sorry, the angular momentum was constant, but there was a change in angular velocity. So was there torque? So what is torque? One of the definitions of torque is the one I erased it, but it was the one dl dt. So this is just like how force is like the momentum dt.
Uh huh.
Torque is like derivative of the angular momentum over time.
Okay.
So of
So
course, this is a derivative, but yeah.
So there would be a change in torque.
Well, is there a change in or we could really talk about this as like the change in L over. So we only have before and after. So what is, or let's even write this like this: L final minus L initial over LT. What's L final minus L initial here? If we had, I mean,
Yeah.
we use this condition, so of course this has to be 0, right? Like by definition, right?
Yeah.
So by
By
change, I mean
initial
before
by
and
final.
after. Yeah, yeah.
So yes, that would have to be 0.
So this would be 0 torque, right? Now, it's a little bit weird, of course, because we had the angular velocity change, but of course we didn't have any added torque. And what that means is that any forces that were involved in pulling them in, like I said, it does require some energy to pull things in. That does require energy, but that's all internal. This means there's no external torques. If you just treat his body alone as a single system, then it does change its own angular momentum, but the total angular momentum doesn't change of the system, basically. So the torque would be 0. This is really external torque, you should say, because it's sort of external from the whole system, which is all we can really say. They don't give us information to talk about the internal.
Got it. Okay. That makes sense. While rotating, the mass is extended. The man drops the masses. Describe the motions of the weights and of the man. What's the man's new angular momentum? Will his angular velocity change?
Oh, I see. So if he's drops them, so he extends them again. So
Yeah.
that would basically so that's basically
Well,
the first.
yeah,
edition.
his mass is extended. Yeah.
Okay.
So drops them.
Right. Okay, that's good. So now, basically, we have basically this term would go away.
Okay.
So so this was the first part, but then he went back to this. So let's forget about this part now.
Okay.
He's just extending them, and now I'm gonna go to like a top view. So I'm gonna erase this real quick, but like so here's the guy's head, and here's the mass here, and the mass here, and he was going like this, spinning like this, and when he lets go at the same time, where is this mass gonna go? What's its velocity going to be? Or even not even its velocity, but just it's like it goes and hits the ground. But if you look from above, what would happen to it?
It would just drop.
It would drop, but
Like
it
it would be in the same position, right?
well,
If you're looking.
it had if he was spinning like this and then dropped it right here, it would just maintain. There's now no more forces on it,
Correct.
but it had some initial velocity because its velocity at that point was v or whatever, and so it would just look. It would just go like this and land like here, and the same exact thing would happen here, right?
Mhm.
Yeah. So you're right. In the y direction, it would just drop. There's it's not nothing more complicated than that. But in the x direction or this direction or whatever, it would maintain its initial flat sort of x velocity.
Okay.
And it would not, it wouldn't go around or anything like that because of course there's no more. It's just Newton's first law now because there was an initial velocity and no forces, so it would keep moving out. Of course, eventually it would hit the ground and friction and it would be at rest. But anyway, so that's what would happen to those things. I guess that's what they want. I mean, if you wanted to find the actual velocity, well, the tangential velocity of something moving in a circle like this, so it was moving like this, where the radius of the circle was d, right,
Mhm.
his length of his arms or whatever, and so the velocity would be related to the angular velocity by d. So I guess this is probably important if they say like what speed would the block be leaving at? They'd be leaving at this speed. V would be d omega.
Okay.
Because omega really is the variable you should sort of. That's the one they give you really. So this is like for anything moving in a circle, the tangential velocity is related to the angular velocity by the radius, and it goes over here. It's kind of hard to remember. This is whenever you have these relations, v equals r omega x equals r theta for angular displacement theta, and a equals r alpha. So these are the relations between the tangential components of the, tangential acceleration, tangential velocity, tangential displacement, whatever, and the angular part. So the angular displacement is just the angle it went. The angular velocity is the angular velocity. This is the angular acceleration. It's hard to remember these because you don't know which side the r goes on. So here's a trick. Oh, the r always goes on the side with the Greek letter.
Okay.
Right? And of course, if you need the other one, you just divide it. So if we were given omega and we wanted to find, if we're given v and we wanted to find omega, we'd of course do this. And in this case, r is d, of course, because that's the radius of the circle, but the blocks are moving around. So yeah, these are tricky to remember which is which.
So then his angular velocity would change.
Yeah, so
Sorry.
then we would have the same setup. Well,
Wouldn't it be that setup without the little m?
yes, exactly. So it would basically be this. Yeah, so yeah, you're right. It would be exactly this setup. We'd have the same equation, of course, but over here, instead of having the masses still count, we would just sort of set them. It's kind of like setting them to 0.
But there would still be the big M.
There was still a big M, yes, because
Not
he's
the
still
little.
rotating.
Okay.
Yes. And of course, he'll have a different.
There wouldn't.
Angular velocity. Because again, we could just solve for omega, and
It would be different, yeah.
we would just get a different number. Yeah, it wouldn't. It's not like it would cancel or anything like that. So yeah, so if he lets go of them, so I'll say like "let's go" is kind of like setting little m to 0. On this side, of course, not on this side, because before he had the masses.
And then, wait, so there would be no,
Yeah.
there would be no D either because he's let go of them.
Yes, exactly.
So that whole thing goes away.
Exactly. This would be there in the before case.
Correct.
Because to find
but
this,
not in the final because even if his hands are out,
it
there's
doesn't
no net.
exactly. They're massless, right? That was the point. So yes, exactly. So it was important that we use this relation still. We can't just set it up without the masses, right? Because of course we don't know anything about the angular momentum. But if we know the before and we have to use this relation, this has a d here, but on this side it'd be like said, yeah, we could rewrite this and just these wouldn't be here anymore.
Yeah, okay.
And then that would be that equation without m's, that little m. Yes. So when you pull things in, push things away, whatever, that changes your moment of inertia. That's fine. Okay. Now in the new system where you have some initial angular momentum, which is just the same as what we just found. It's this side. This is our initial angular momentum. But now we want to say that, well, when you release the masses, what's actually changing? Actually, nothing is changing, right? I mean, the system looks like it's changing, but what's happening is that you have some, so this is L final. They're equal because there's no external torques, so that part was.
Yeah.
I'm glad that was bothering me sufficiently. So the final angular momentum is the same, but we can break it into the components, which is your component. So this is L of the person plus L of the masses, right? Because it's just breaking into two components. But of course, the person's just going to maintain. Now we could break this down further if we want. Yeah, and so L of the masses, now they have some linear momentum, P, or we could say linear velocity. It was actually this. This is why I wanted to keep this, because it's this velocity that they leave at. So the angular momentum of the masses is R cross P. Now, of course, these are changing. R and P are changing, but we could just take the moment that they leave, which is going to be D times mv. Right, and there's two of them, so it's 2. Or you could say 2m, right? So what I did here is I just took R cross B. They're perpendicular anyway, so don't worry about the cross product, but it's the distance is D, the R, the radius is D. I'm sorry, again, when these fly off, they have a constant angular momentum. Sorry, it really should use this picture. When they fly off, their angular momentum is exactly what it was at this point. It doesn't change. They're not moving in a circle anymore. The things don't have to move in a circle to maintain their angular momentum. There's no torques acting on them when they go in a straight line, and so they have a actually also there's no torques on them when they were going in a circle, right? Because the forces were inward in the same direction, so the torque, the R cross F, was still 0. Anyway, so they have no torques on them, so the angular momentum, they still have the same angular momentum when they go on forever, and then of course whatever hit the ground. So we can talk about them as R cross P. It's the same thing. Okay. Now R is the distance. Let's do the angular momentum right when they left, because that's easier. The distance is D, the momentum is mv, and there's 2 of them, so we just have to do 2. So it's L mass 1 is just this, and we had 2 of them. L of the person is I, which is 1/2 m r squared. This is the same times omega. Okay, and you can kind of see.
Now, would you plug D in for R?
Oh, yes, yeah. Yeah, sorry. So now we want, yes, thank you. That's what I was missing. So now, of course, this has a variable V, which we don't really know much about. So let's replace it with d omega, because d omega was, it's not a derivative, it's the letter d.
D, yeah.
Now that's going to take this d and make it squared. Omega, now omega is the angular velocity that's the same as this one, right? Now notice that it's actually not moving in a circle anymore, but we can still write it as omega. It's just a variable, right?
Okay.
Now this is identical to this. So notice that even though the masses were not moving in a circle anymore, so we had to use their non-circular form. Okay. But by some algebra and stuff, we actually got this, which this is identical. This, if we can rewrite this as 1/2 m r squared plus 2 m d squared all times omega. This is identical
to
that.
Okay.
So it's angular. Yeah. So, yeah, good.
Do we set that equal to the initial?
We actually, now that what we showed is that because the initial,
they're the same.
They're the same. So omega, whatever it was, is exactly the same, right? Because this omega here is just the same as that omega over there.
Got it. Okay.
We basically showed that even though they're let go, and we use this other formula for a thing moving in a straight line, of course they're all always true, but this is easier, we actually got that it's the identical form to originally, not this step, obviously this originally, and so basically the two things I said could be either true, they're both true. The angular momentum is constant, and the angular velocity of the person is constant. And let's actually, yeah, okay. Let's think about that statement. So that what I just said is the angular momentum is the same before and after, and the angular velocity is the same. Now that can't be true for a single object, right? Because if well, it can, but then everything like that's just identical situation, right? If L is the same, if L is conserved, and one of these changes, the other one must change the opposite, right?
Okay.
But in this case, we actually had things were basically showed that when you let something go, literally nothing changes. It's actually not even anything. So therefore, every single quantity is the same. Of course, the masses are no longer spinning anymore, but they still have the same angular momentum as they did. Basically, he has some fraction of the angular momentum, which is this much, this times this. He has some fraction of the original full object. But of course, he has the same fraction as he did before. It's just that before we didn't break into fractions. But anyway.
Okay.
Okay, I hope that
Yes.
makes a little sense.
So now this, I cross it out.
Yeah, so the part where I was saying that the L changes, none of that's true. In this entire situation, there's no external torques.
Yeah.
So L is always constant in all of these situations. In one case, we actually really had a real thing happening. We had something really changing. Yeah, when you pull things in, the I is literally changing.
Yes.
That's a serious, real thing. The L is constant, but the I is changing. In the second case, we had actually, seemed significant that you let go of some masses, whatever, but actually nothing really happened. It's the identical situation.
Okay.
Yeah. Does that make sense?
Yeah. No, definitely.
Okay. All right, I'm gonna erase all this.
You're good.
Do you have anything else?
I don't know.
You don't have to ask. I mean, I encourage you to ask questions, but
Yeah.
don't feel bad if you don't feel like you have to keep me busy right now.
I think I'm good.
Because the other ones I think we did some other day, I think, right? Or they're on video or something. The homework, the last two homework questions or whatever.
Yeah, I think I'm good with the last two.
Okay,
But
good.
I'm not sure.